Okay, we're talking about acids and bases here. Now our objectives for this unit are to learn about the models of acids and bases. We're going to understand the relationship of the conjugate acid-base pairs. We're going to understand the concept of acid strength and understand the relationship between acid strength and the strength of the conjugate base, and learn about the ionization of water. Now down here what you have is water reacting with hydrochloric acid here. And what happens is that this H really likes those electrons right there, and this proton is what I call it. Also, by the way, at the beginning of this unit, you should know that I call it a proton, or people in chemistry do, because if you have a normal hydrogen atom, what you'll have is you'll have a proton with an electron floating around it in the electron cloud. And what happens is when you give away, or when this hydrogen atom, I'm just going to say normal H, when he gives away that negative electron, what happens is when you give away a positive, or I'm sorry, when you give away a negative, you become more positive. And if he just gives away one electron, he becomes H+. But now that that electron's gone, all he is it's just a single proton floating there. So I'll toss around the term proton, but when we look at how we write these equations of the acid-base neutralization reactions, just know that when I say it donates a proton, I'm talking about capital H here. All right, hydrogen. But yeah, this hydrogen is overall more positively charged than that really greedy chlorine atom over there. And what happens is hydrogen says, hey man, you're not sharing any electrons with me, so he leaves and attaches that out of oxygen. And what you get after that, it's called a hydronium atom, and then you get a chlorine ion floating there with that. Not that he's just floating around, but these guys are going to dissolve in the solution. Now in class we talk about two different models. The Arrhenius model is where an acid produces hydrogen ions in an aqueous solution, and then a base is by definition produces hydroxide ions, and you'll see in a second why he thought that all bases had hydroxide ions or produced hydroxide ions. He was pretty close, by the way. In his model he had donating protons here, and then a base would donate hydroxide ions. If you take a look, that when you put a positive H with an OH, you get H2O, by the way. So that should be noted there. But later on, the Bronsted-Lowry model came, and what they realized is that bases did not just merely have to be considered the ones that produce hydroxide ions, but bases are anything that just accepts a proton at all. For example, if you have, we'll talk about ammonia, where you have NH3, he's actually a weak base, and what happens is he'll pick up a proton, and he'll become ammonium NH4+. So, by the Bronsted-Lowry definition, he's actually a base as well. So an acid is the same as donating protons, but a base in the Bronsted-Lowry model is anything that accepts protons. Okay. Now, the next thing I want to talk about is conjugate acid-base pairs. Hydrochloric acid here is a strong acid, and if you put acid into water, what will happen is, like we said before, that the acid donates protons. Well, this hydrochloric acid is going to get rid of one of these H's. He's going to give this H to the water. And so as you can see, if you look at the second side of this, you have hydronium here, which says, oh, okay, this should be an indication, well, if you have water here, did he not just accept that proton? So that makes him the base, because he accepted it. Now, water is a special substance. We already talked about how essential water is to life on planet Earth, and almost all functions, life forms need water. But one unique thing about water is that it's neutral, and it can act as an acid or a base. So if you put an acid into water, it'll act as a base. But if you end up putting a base into water, he'll act like an acid. Now conjugate by definition is the opposite or the inverse. I don't know if in math class you talk about multiplying by the reciprocal or the conjugate, but it's just basically you take a fraction and multiply it by the inverse. But anyway, if this is your acid and he donates a proton, he's going to end up looking like this. He's going to be a chloride ion, and you're going to have hydronium. Now, if you just blot out this side and you just started off with the products here, what would you expect? Would you expect chlorine ion or the chloride ion to act as an acid, or would you expect him to act as a base? Would you expect him to act as an acid or a base? Well, actually, if you just started off with these ingredients over here, what would happen is this hydrogen would have been donated to him. And you would just have the reverse reaction going back in the other direction. But being that he would act as an acid in the product side, you're going to call him the conjugate acid, and you're going to call this guy the conjugate base. Alright, and that's why they call it a conjugate acid-base pair. Do you see how they connected these two with a little bracket, and then down below they connected these two with a little bracket, because this is an acid and a conjugate base pair, and here's a base with a conjugate acid, and that's what I want you guys to do on the homeworks. Okay, now looking up here, what I have here is a chart that demonstrates what a strong acid is and what a weak acid is. We classify them by their properties. Now, a strong acid and a weak acid, they don't necessarily hurt you more than one more than the other, but it's all about the concentration. But a strong acid, by definition, is an acid that dissociates completely, meaning that when you put it in solution, you'll get 100% protons donated, or really close to 100%, and 100% of the negative ions floating around. Okay, so a weak acid is different. When you put about the same amount, the same molar amount into a solution, what will happen is only a portion of it will break up into the H plus and B minus. You see how this is all positive H, and this is just a little bit of positive H? Well, this is the portion that is going to act as an acid. This is what's going to change the pH. So that's why a weak acid is classified that way, because it only partially dissociates, and a strong acid completely dissociates by definition. Now, again, I was going to say that the weak acid, you can actually have it be more dangerous in a lab if you have a really, really high concentration. Just imagine instead of starting with this amount, like the same amount as the strong acid, imagine if like you started off with a whole bunch of your weak acid. Well, you can have a portion of it, be even more concentrated in terms of its protons. Okay. Now here is a list of various strong acids. You have hydrochloric acid, nitric acid, sulfuric acid. Those are the common ones, and you have some weak acids here. That's acetic acid. I'll talk about that in class quite a bit. That's in vinegar. You got your strong bases here. Basically any of your alkali or alkali earth metals paired with hydroxide, there's some more there, will be considered a strong base and dissociate completely. And then here's ammonia and ammonium hydroxide. Those are weak bases. Okay. Now I will ask you guys in class to be able to say, hey, well, if hydrochloric acid is your acid, what would be the conjugate base? Question mark. Well, what you have to do is realize, well, if this is the acid, doesn't an acid donate protons? And you say, okay, well, if he got rid of a positive H, would he not be a chloride ion by himself with a little negative? Because he got rid of an H plus. Okay, he got rid of it. Bye-bye. So there, you got your conjugate base, and you could do that for any of these, like this one, like nitric acid. You would start off with HNO3, and then end up with NO3 minus Okay, now here's your H2SO4. That's sulfuric acid. You see how he has two H's there? That's what they call a diprotic acid. The diprotic acid means that he can donate not just one but two different protons. So, and he's got to act the same way. It's just his first step is going to be just HSO4 minus. And then if he donates a second one, he's just going to be SO4 minus 2. And does that not look familiar, guys, from our nomenclature unit? That is sulfate. Okay, and in the opposite sense, if I ask you guys, hey, here's a base, NaOH, what would be the conjugate acid? Now, if he accepted an H, he would end up being H2O as your conjugate acid. Okay, but he would actually have to have that sodium ion get kicked out. So what I'm going to do in the worksheets is I'll say, hey, here's OH, or hey, here's SO4 minus 2. What is the conjugate acid to these two bases? Well, bases by definition accept protons. So when this guy picks up one, like before, like I just showed you, he's going to be H2O, and he's going to have a neutral charge. If you guys mess up the charge, I'll have to count it wrong. But if you're -1 and you gain a positive 1 charge, you neutralize and you're going to be happy. If you are SO4 minus 2 and you gain 1 positive charge, you'll be HSO4 and -1. Okay, so there you go. That's your basic acid-base intro. Oh, the last thing I would like to say is that an acid is characterized by a sour taste. If you guys notice that citric acid is in a lot of drinks and candies and whatnot, an acid is going to taste sour, and bases are going to taste bitter. Like soap. I don't know if any guys have a foul mouth and your mom or grandma, cleaned your mouth out with soap, but it tastes really, really bitter. Okay, well there you go. Those are your acid-base notes, and enjoy.